In this lecture, we will be learning about the concept of Taylor series. Recall the idea of power series representation. Power series representation is a way of representing a function f of x as a power series on an interval of convergence. The question that we're going to focus on here is if we're given f of x with derivatives of all orders, can we represent it as a power series? Can we use f to generate a power series that it will actually be equal to on an interval of convergence? The first step in this process is to assume that we can do it. Assume f of x can be written as a power series, and let's take a look at what it should be like. Well, it should be like this. F of x would be equal to, this is just a generic way of writing a power series, straight from the definition of power series, for all x in the interval of convergence for that power series. And let's think about what we would need to find. If we look at the terms in our power series here, n, this is the index of summation. So that comes just from this n here, having it change values, 0, 1, 2, 3, 4, so on and so forth. A is a parameter. It's a parameter that we choose. X is the variable. That leaves one term, C sub n. So this we must solve for. If we can solve for C sub n, then we will have found a power series representation for f of x. So let's look at that and actually derive what Cn should be. So we rewrite our power series representation equation for f of x, and let's write out some terms. So the first term, when n is 0, we have C0 x minus a to the 0, or C0 times 1. When n is 1, we have C1 x minus a to the 1. When n is 2, we have C2 x minus a squared, and we continue this, C3 x minus a cubed, C4 x minus a to the 4th, so on and so forth. Well, recall that f of x has derivatives of all orders. So let's take some derivatives. When we take the first derivative, we note the derivative of this first term, which is just a constant. This first term has derivative 0. The second term will have derivative C1, because note, if you multiply this out, you have C1x minus C1a. So the derivative of this term with respect to x is C1. For this term, we have a power rule problem. The 2 comes out front, and we get 2c2 times x minus a to the 1, times the derivative of the inside function with respect to x, which is, of course, 1. For the next term, we have 3c3 x minus a squared. For the next term, we have 4c4 x minus a cubed, so on and so forth. So that gives us an expression for f prime of x, but we can keep going. Let's differentiate f prime to get f double prime. So the derivative with respect to x of c1 is 0. The derivative of this term, we'll just have this constant out front, 2c2. For this term, we have another power rule computation. The 2 will all come out front. We'll reorder it. We'll write it as 3 times 2, C3, x minus a to the 1. The derivative of this term, we have 4 times 3, C4, x minus a squared, so on and so forth. We do it again. Differentiate f double prime to get f triple prime. The derivative of that first term is 0. The derivative of the second term will just be this constant 3 times 2 times C3. For this term, we have power rule again, so the 2 comes out front, and we get 4 times 3 times 2 C4 times x minus a. And so we're starting to see a pattern. If we were to do one more, the fourth derivative, the derivative of this term, which is a constant, would be 0, and we would get 4 times 3 times 2 C4. And the next term would be 5 times 4 times 3 C5 x minus a. So we notice something very convenient here. Because remember, the point of this is to try and solve for the CNs. That means we need to solve for C0, C1, C2, C3. We need to find all of them. But we notice something very convenient about each one of these equations. And that is, what happens if we plug in x equals a? And if we do that, notice what happens to the first equation. This term will drop out as 0. This term will 0 out. In fact, every term except the first will 0 out. If we plug a in for x in f prime of x, we get a similar phenomenon. Every term will drop out except for the first. If we plug in x equals a for f double prime, we see something similar there. This first term survives, and the rest drop out. And we see that happens in every case, even if we continued. Fifth derivative, sixth derivative, seventh derivative. Plugging in x equals a results in just one term for each. But let's try and find a pattern. Notice that what we have here is 4 factorial times C4. To get that, we should technically add a times 1 here. If we add multiplication by 1 here, this term has a 3 factorial. Here, if we add multiplication by 1, we have 2 factorial. Here we can think of there being a 1, but 1 is equal to 1 factorial. And if we want to keep the pattern going, the definition of 0 factorial is equal to 1. So we could call this one 0 factorial. And now we've identified a very nice pattern that for each of these derivatives, when we plug in x equals a, we get one term, which is actually n factorial, right? This is the fourth derivative. So in this case, we want to think of it as n equals 4. So we have n factorial times the coefficient Cn. So we've now identified the pattern. This is our equation for n going from 0, 1, 2, 3, so on and so forth. But recall that what we want is the coefficient Cn. But we now notice we can solve this equation. Remember, it's key to keep in mind that we are given f of x, and we can compute its nth derivative. So this on the left-hand side, we know. n factorial, we know. So this means that we can solve for Cn as the nth derivative of f evaluated at a over n factorial. Now that we have this, recall our power series representation equation said that f of x was equal to the sum, n going from 0 to infinity, of c sub n times the quantity x minus a to the n. And we can now plug this c sub n in to our power series. And we get sum n going from 0 to infinity of the nth derivative of f evaluated at a over n factorial times the quantity x minus a to the n. So if f has a power series representation on some interval of convergence, this has to be it because of what we just went through here. Remember our premise here. We said assume f of x can be written this way as a power series, and then we deduced what these values would be for the coefficients. So this has to be it. And this is what we call the Taylor series generated by f at x equals a. So this is our Taylor series here. Written out, we see the first several terms written here. So if f can be written as a power series, this is it. And that's our Taylor series. Let's look at an example and see how this works. So consider the function f of x equals 1 over x, and we're going to use x equals 2. So that is our a value. That is our unknown in our Taylor series. Again, looking at this, a is a parameter, n is the index of summation. So that nth derivative of f at a, that's our unknown. Once we actually figure out what that is, we then have the Taylor series for f at x equals a. So let's see if we can figure out what the formula is for the nth derivative of f evaluated at 2. So let's start taking some derivatives and see what we get. So initially, we have f of x being 1 over x, or x to the minus 1. So f prime of x, using power rule, we have minus 1 x to the minus 2. F double prime will be minus 2 times minus 1 x to the minus 3. And one might say, why not simplify this? Why not write that as 2 x to the minus 3? And the answer is simplifying in these types of computations makes things more difficult, because the key is to identify the pattern. So let's do the third derivative. Minus 3 times minus 2 times minus 1 x to the minus 4. For the fourth derivative, minus 4 times minus 3 times minus 2 times minus 1 x to the minus 5. And we can go a little bit further because we note this looks like we have a factorial growing. And we can also now notice the pattern of minus signs. So f prime of x, keeping in mind our n value, this would be the case for n equals 0. Here's 1, 2, 3, 4. The n as in the nth derivative of f. So here we have f prime of x is minus 1, x to the minus 2. Let's think of that as minus 1 to the 1, x to the minus 2. For the n equal 2 term, we have two negative signs. So we could say we have minus 1 squared times 2 times 1, x to the minus 3. For the n equal 3 term, we have 3 copies of minus 1. 3 times 2 times 1, x to the minus 4. And in this case here, for n equals 4, we see we have 4 copies of minus 1 times 4 factorial, x to the minus 5. Here, for the n equals 3 case, we see we have negative 1 cubed times 3 factorial, x to the minus 4. For the n equal 2 case, we have minus 1 squared times 2 factorial, x to the minus 3. For the n equals 1 case, we have minus 1 to the 1. And we can then think of it, to try and again discern the pattern, put a 1 in here. 1 is equal to 1 factorial, so we have 1 factorial, x to the minus 2. And in this case up here, we have a positive 1, so we could think of that as minus 1 to the 0. And remember, 0 factorial is 1, x to the minus 1. And so we now see our pattern. It looks like what we have here is the nth derivative of f evaluated at x. Think about your n's. In this case, we had n equals 4. So we have minus 1 to the n times n factorial x raised to the negative n plus 1. But recall, that's not quite enough because we have to evaluate each of these derivatives at 2. So we can say the nth derivative of f at 2 is minus 1 to the n times n factorial times 2 to the negative n plus 1. And we can make a column here where we can evaluate each of these derivatives at 2, just to see how this works out. So for this first term, we'll have minus 1 to the 0, 0 factorial, 2 to the minus 1. Here, we get minus 1 to the 1 times 1 factorial, 2 to the minus 2. Minus 1 squared times 2 factorial, 2 to the minus 3. So we're identifying the pattern. And this is exactly what we need. We summarize that here. So we see we've identified this nth derivative of f evaluated at 2 to be this n factorial 2 to the negative quantity n plus 1. Which means we now can write down our Taylor series. Sum n goes 2 to infinity. That nth derivative of f at 2 is n factorial times 2 to the negative quantity n plus 1 over n factorial times the quantity x minus 2 to the n. And we see, conveniently, the n factorials cancel. We can thus write this sum n going from 0 to infinity. That 2 to the negative quantity n plus 1 we can bring to the denominator as 2 to the n plus 1. In the numerator, we have x minus 2 to the n. We can clean this up a bit more. Notice we can write this as the sum n going from 0 to infinity of x minus 2 to the n over 2 to the n times 2 to the 1 using our rules for exponents. And we can thus factor out that 1/2, that lone 2 in the denominator, and write what remains as the sum n going from 0 to infinity of x minus 2 over 2 all raised to the nth power. And this is our Taylor series, generated by f. Remember that f is 1 over x at a equals 2. So this is our Taylor series. And remember, the idea was, can we write f of x in this way as a power series on some interval of convergence? Well, we should figure out what the interval of convergence is in this case. And we note that this series is a geometric series. With r equal to 2 minus x over 2. And recall the conditions on convergence for a geometric series is to have the absolute value of r smaller than 1. That's if and only if the absolute value of 2 minus x over 2 is strictly less than 1, and we can flesh that out. Another way to write this inequality is to say that we have minus 1 is less than 2 minus x over 2 is less than 1. Let's multiply everything by 2. So we get minus 2 is less than 2 minus x is less than 2. Let's then subtract everything, subtract 2 from everything. So we get minus 4 less than minus x less than 0. And if we multiply everything by minus 1, the inequalities reverse, and we see we get an interval of convergence of 0, 4. And note, it is not an accident a equals 2 is the midpoint of this interval. Okay, well, we have said if f of x equals 1 over x can be written as a power series, this has to be it as a power series where a equals 2. Let's check that it actually converges to 1 over x. We know that a geometric series that does converge, like this one, converges to the first term over 1 minus r. So we know that our first term in this case is the case when n equals 0. So we get 2 minus x over 2 to the 0, or 1. And 1 minus r will be 1 minus the quantity 2 minus x over 2. And let's simplify this. So this will be 1/2. Let's change this 1 to a 2 over 2. So we have 2 over 2, and we can distribute our minus sign. And we'll get plus x minus 2 over 2. Our denominator thus becomes we see that this 2 and this negative 2 will cancel, and what remains is an x over 2. Which we can write 1/2 times 2 over x, or 1 over x. So we see that it is in fact the case that if we choose x from the interval 0, 4, that this power series, this Taylor series, is another way to write or represent the function 1 over x. So think of it like the same thing in disguise. So this is Batman and this is Bruce Wayne. So we have found this different version of 1 over x on the interval 0, 4. And again, note that our a, which is 2, happens to be the midpoint. So we will explore this further, and we will see why this really turns out to be so critical. This is going to be extremely useful, and we'll actually see more about why this a value is important for this when we get into the concept of the Taylor polynomial. Because where this is going is to say, suppose we know this is the case for x in this interval, but we want to approximate 1 over x using a partial sum of this series. Maybe we use the first 3 terms, or the first 2 terms, or the first 5 terms. And we'll explore that in the lecture on Taylor polynomials, which is coming up.